Okay, hello, we're recording. Hi, my name is Sergio Garcia. I'm just going to quickly go over some important sort of equations and general thought processes for chapter 5, which is essentially just applications of chapter 4. So we're going to start off on the left. Free body diagrams essentially are really useful when looking at a problem and assessing the forces that are applied to it. So typically in any given problem, you'll get multiple different free body diagrams, because let's say if it's a situation where it's like a box dangling by a cord, in situations such as those, you're going to have a free body diagram for the string itself, or like the cord or rope holding the box, as well as the box itself, and in some cases even the ceiling, depending on what the question might be asking you. If I get my spotlight pen right here, I'm going to choose this color. So this is just a general format. This is not for a specific question. For here, I gave us some givens just to make it make sense. So for example, if the situation calls for it and first thing you would do is draw your free body diagram, like the numbers are arbitrary. It doesn't matter for the specific example. If you were trying to calculate the sum force of X, that would be any force that's moving horizontally, right? And we have two particular forces like that, right? In this situation, we're saying that this is tension. This could just be f of x. It just depends on the problem. So it would be tension plus negative friction, and that is because friction goes in the negative direction. So it would essentially end up being your tension minus your friction. And then for your y, it's typically a collision of your normal force, as you can see, because it's vertical. Your normal force compared to your weight, which, if you remember from the last video, weight is your mass times the acceleration of gravity. Oh, hold on. In this situation, oh no, I didn't mean to do that. This could end up being negative 9.8, because that's gravity. So I'm just going to flat out erase that, because that's negligible when you understand how weight works and how gravity works. Your acceleration here would just be your gravitational constant, which in this case is 9.8. So yeah, that's like general stuff for free body diagrams. Of course, they vary. Sometimes you'll have a question that looks kind of like this, where like you'll have oh no, hold on. Let's say you have a ramp like so, right? They could give you any arbitrary angle theta, and you could have like a box on it with a tension. Let's say it's a string, right? This is your tension, your normal force, your weight will go down like this, and you might end up having to solve using components of vectors to find out what your W is, so that you can find out the downward force being placed on the object. And then nextly, we can talk about friction. So in statics and dynamics, you have two coefficients of friction. You would have your hold on. Yeah, you would have, if you look at the top right over here, you have this, which is a general rule of thumb, but let's say you had mu kinetic, which is essentially your coefficient of friction kinetic when something is moving. It'd be your kinetic force that the object is exerting, let's say in the x direction, and then divide that by the force exerted in the y. And that works for static as well. It just so happens that to find these, you need to first understand what these forces are, and then it's just a ratio between them two. That's why it's the coefficient of friction. And yeah, typically if it's static, the coefficient will be pretty large. And if it's kinetic, it'll be kind of smaller. And then nextly, we have just a permutation of the formula F equals mass times acceleration that we learned in the last video. If you want to find the acceleration of, let's say, acceleration to the right, like, like right or left, the horizontal acceleration, you would do the net force in the x direction over the mass of the object in order to find its acceleration. And that'll be important in certain problems. And then finally, we have circular motion. I'm not going to cover it too extensively because it's the general same vibe of this. The only difference being that your free body diagram is going to look slightly different. But what's important is to find your net force. You have to use this equation because it takes into account the velocity of the moving object as well as its radius of the circle, which contains it. And in situations where there's tension, that radius is very important because the tension makes it so it can't exude past that radius. And those are like just general concepts. I'm not too in depth on these in terms of explanation. This is just a quick little review just to get these examples out here. So yeah, thank you for your time.